This lecture is the second part of our discussion of acceleration. We would like to know how to determine if an object is speeding up or slowing down. When an object is speeding up, the acceleration and the velocity vectors point in the same direction. When an object slows down, the acceleration and velocity vectors point in opposite directions. An object's velocity is constant if and only if its acceleration is zero. In the motion diagrams to the right, one object is speeding up and the other is slowing down, but they both have acceleration vectors towards the right. In this quick check, a cyclist riding at 20 miles per hour sees a stop sign and actually comes to a complete stop in 4 seconds. He then, in 6 seconds, returns to a speed of 15 miles per hour, which is his motion diagram. Well, we can break this motion up into two parts. In the first part, the cyclist is slowing down, and in the second part, he speeds up. So we can eliminate answer A and answer D, because in neither case is the object or the cyclist slowing down in the first part. We see in B that the cyclist is slowing down because the acceleration vector is pointing in the opposite direction as the velocity vectors in the first part. And that's also true in the second part, in answer C, that the cyclist has its acceleration vector in the opposite direction as its velocity vector. So we have to decide between B and C. So let's look at the second part of the motion. In the second part of the motion, in B, the acceleration and velocity vectors are in the same direction. And that's also the case in case C. So we can't tell yet which is the correct answer, B or C. So let's go back to the statement of the problem. The problem states that the cyclist starts at 20 miles per hour, and then at the end of his trip, he has a speed of 15 miles per hour. So his beginning velocity vector must be greater than his ending velocity vector. And that's the case in choice B, but not in choice C. So the answer is B. We'd like to look at tactics for determining the sign of the position, velocity, and acceleration. The first two drawings here show the position of an object. In the first one, if the position is to the right of the origin, then the position is positive. And if it's to the left of the origin, then the position is negative. In the case of velocity, if the velocity vector, if the motion is to the right, then the velocity in that direction is positive. And if the motion is to the left, then the velocity vector points to the left and is negative. If the acceleration vector points to the right, its acceleration is positive. If it points to the left, it's negative. Now this text box describes motion in the horizontal direction. We continue with our discussion, but now with motion in the vertical direction. Then, if the position is above the origin, then its position in y is greater than 0. If it's below the origin, it's less than 0. If the object is moving upwards, its velocity vector points upwards, and the magnitude of its velocity is greater than 0. And it's negative if the velocity is pointing down, then it's moving downward. If the acceleration vector points upward, then its magnitude is positive. If it points downward, it's negative. So in summary, the sign of the position, x or y, tells us where an object is. The sign of the velocity tells us which direction the object is moving. And the sign of the acceleration tells us which way the acceleration vector points, but not whether the object is speeding up or slowing down. To determine that, you need to compare the direction of the acceleration vector with the direction of the velocity vector. In Quick Check 1.7, a ball is tossed straight up in the air. At its very highest point, the ball's acceleration vector, a, is pointing up, is 0, or points down. The answer is it points down. And as we can see from the inset drawings and the figure to the right, the acceleration vector points down as the ball rises at the highest point and as it falls. Let's examine these inset drawings. First, the one on the left, this drawing here. If we compare two segments as the ball is going up, then the subsequent segment, the final, is pointing up. Then to find the change in the velocity between it and the preceding segment, we add to the final velocity the negative of the preceding segment. And then from that we find the change in the velocity between the two segments, delta v, and this shows that the acceleration is pointing downward in the opposition to the velocity vector, which is pointing upwards. So that makes sense because we know that it's slowing as it's going up, so we know the acceleration vector must point in the opposite direction as the ball goes upward. Now if we consider the inset drawing over here to the right, this is looking at segments of motion of the ball going down. If we compare two subsequent segments using the same technique, we add to the final velocity segment the negative of the initial velocity segment to find that delta v is pointing down. And the acceleration vector must be pointing down also, but this makes sense because we know it's speeding up as the ball goes down. So the acceleration vector and the velocity vector must be pointing in the same direction. Then if we look at the two segments at the top, that is the segment before the top and the segment just after the top, If we add to the velocity vector just after the top position, which is pointing down, to it we add the negative of the velocity vector just before it got to the top, then we see that the delta v is pointing down, and so the acceleration is pointing down. So, as stated to the left, in fact, the acceleration vector points down as the ball rises at the highest point and as it falls. In Quick Check 1.8, the motion diagram shows a particle that is slowing down. We see that because the acceleration vector is pointing to the right, while the velocity vector is pointing to the left at each dot. The Quick Check question states that the sign of the position x and the sign of the velocity vector are which of the four choices? Well, we see that the position vector at each dot is to the right of the origin, so its position at each point is positive. And between each pair of dots, the velocity vector is pointing to the left, so the velocity is negative. So the correct answer is choice B. In the next quick check, the motion diagram once again shows a particle that is slowing down. The sign of the acceleration, a sub x, is positive because it's pointing to the right. And that concludes this video. See you next time.